Today we are going to talk about Newton's second law, and so that's what our notes are going to be over. But before we get into that, I explained kind of what the free body diagram would look like for this warm-up question. But let's go ahead and diagram it on the screen. So you'd have, again, your weight, always a good thing to add. If you're on or near Earth or a planet, you should always have that. Fn is that support force from the ground. I did draw these so that they were equal and opposite to each other because the carts are not experiencing any motion, much less acceleration up or down. So they do need to be the same magnitude whenever we draw them. We're going to get more into that discussion today. And then, of course, we have the applied force. This is Edwin's force that he's pushing on the carts to the left. It says to neglect friction here, so the only other force I included was the force of cart B on cart C. Okay, and so that is the last force that I included here. If he does move them from rest, then I would want to draw this applied force so that it was longer than this one to give me a net force that would cause that acceleration. So again, just some practice before we jump into the notes. But let's go ahead and talk a little bit about Newton's first law before we get into the second law. Okay, so again, as a reminder, Newton's first law of inertia stated that an object in motion will remain in motion with a constant velocity, and an object at rest will remain at rest unless acted on by an outside unbalanced force. And I asked you questions like this about these two boxes, one of them full of books, the other one empty. It's a different question this time, though. It says, let's say I exert 200 newtons of force on both boxes to accelerate each from rest to the right across the floor. If friction exists, draw a free body diagram for each. Okay, and so you could draw a free body diagram for both of these boxes. So box A, I have the same forces on each of them, but you'll notice a couple little differences here, and I don't have numbers on it. But I do know that because box A has more mass, it also has more weight. And so I drew this FG vector longer for A than I did for B. And again, my Fn, my normal force, is equal and opposite to my Fg whenever I'm on a flat surface. And guys, that's not always going to be true. I'm not always going to be on a flat surface. Okay, so sometimes they won't be equal, but for now they are. And then over here is a similar situation, but these vectors are a little shorter because this has less weight to it. And then because of that, because Fn is smaller, the force of friction is going to be smaller as well. Again, our equation for that is mu times Fn. So if you have a smaller Fn, you will have a smaller force of friction. So again, you should be able to draw free body diagrams to help you answer questions as well. Okay, which would accelerate more if the same force was applied to each? I asked y'all this question once already whenever I was illustrating or going over the definition of inertia. Okay, and so of course, if you apply the same amount of force to each, you're going to get more acceleration from box B because it has less mass. Okay, and therefore it has less resistance to acceleration. It's easier to move it. But this one would accelerate more, this one would accelerate less. And it says, what if box A was pushed a second time with twice the force? How would its acceleration compare? So now instead of talking about mass and how that affects acceleration, we're answering a question about how the amount of force we use affects the acceleration. So what do you think is going to happen if you push something twice as hard? Do you think it's going to accelerate more or less? It's not a trick question. I heard somebody say it over here. More. Okay, yeah, you're going to have a greater acceleration if you have more force. And again, you can see that in the equation we're going to talk about today for Newton's second law, because that's what we're kind of getting into here. Okay, is that there is a relationship between the amount of acceleration an object experiences and the force applied to it, or the mass of it, and those are going to affect how much acceleration you have. This is that equation. So this is Newton's second law. Please go ahead and write it down. It is F equals ma, or more precisely, F net equals ma. The net force, when we talk about F net, is going to refer to the sum of the forces acting on the object. So if you have more than one, you're going to have to get the sum of those forces. You're going to add those vectors together. Okay, but Newton's second law states that the acceleration of a system is directly proportional to the net force acting on the system and inversely proportional to the mass of the system. We just talked about both of those relationships on the previous slide. We said, hey, if the force is the same but we have less mass, how's the acceleration going to compare? And you guys said, well, that empty box is going to accelerate more because it has less mass. Again, that smaller mass, greater acceleration, we're talking about this inversely proportional relationship. Okay, whereas when I asked you about pushing twice as hard, we're talking about this directly proportional relationship between force and acceleration. Okay, so those are the relationships you need to know. You can see them by looking at the equation. F net equals mass times acceleration. And then as a little note, you might want to write this down, but acceleration is also a vector, as is force, and so your acceleration will occur in the same direction as your net force. If you have a net force to the left, your acceleration will be to the left. If your net force is down, your acceleration will be down. If you don't have a net force, you don't have acceleration. Okay, but your acceleration will occur in the same direction as your net force. So, let's talk about the variables in this equation. We have force, mass, and acceleration. Okay, forces, as a reminder, are measured in units called newtons, which are abbreviated as a capital N. 1 newton is the same thing as 1 kilogram meter per second squared. That is a much longer unit to write, but it is the same thing, and that might be helpful to you if you're trying to figure out how to cancel the units when you're doing a calculation. If you're trying to figure out what your units should be at the end. Okay, but a newton is a kilogram meter per second squared. The M in this formula is mass. The masses must be in kilograms, and again, that's because the newton is a kilogram meter per second squared, so in order for your units to cancel appropriately or to end up with the right unit in the end, okay, they need to match up. And so your masses, when you put them into this formula, must be in kilograms. If they're not, you have to convert them. You cannot plug grams into it. It will not give you the right answer. If you need to write down the conversion factor, 1 kilogram is equal to 1,000 grams. The A in my equation is acceleration. Accelerations are measured in meters per second squared or meters per second per second. So again, Newton's second law is summarized by this equation, F net equals ma. All right, so let's look at a couple proportional reasoning questions. Okay, so this one says a 2 kilogram object is pushed with a 10 Newton force, causing it to accelerate from rest. If the mass is quadrupled, what happens to the acceleration? We've already kind of talked about this, but let's go over some more definite examples with some numbers in them. But if I have 4 times as much mass, if I quadruple the mass, what happens to acceleration? Yeah, decreases. By how much though? How much will it be? What factor? Factor of 4. So it's going to be 1/4 as much. Okay, so if you have something with 4 times the mass, okay, you're going to get 1/4 the acceleration from an equal amount of force. Okay, again, that's that inversely proportional relationship we were talking about. The second one says if the net force is cut in half, what happens to acceleration? If you have half as much force, half as much acceleration. Okay, again, you should be able to do these pretty quickly, hopefully, once you get the hang of it. What if you do both of those two things? What if you have 4 times the mass and you have half the net force? Yeah, you would just, again, apply both of those changes. You could you'll high-fiving each other. All right, that works. Yeah, you'd have 1/8 the acceleration. So you guys will see questions like that, or maybe you already have if you've been going through your problem sets, your task options rather. You're going to see some proportions in there. Okay, so again, this is the same thing I already had on my screen earlier. Acceleration of an object is directly proportional to the net force acting on the object and inversely proportional to the mass of the object. If you want to add these 2 bullet points underneath it to illustrate the relationships that we just went over, you can, but larger net forces cause larger accelerations when masses are equal. Larger masses accelerate less when forces are equal. We just talked about those 2 relationships, but that's that. Again, your net force and acceleration, that's the directly proportional relationship it's referring to up here. This is your inversely proportional relationship, larger masses, less acceleration. But again, if you want to list it out, you can. Okay, so let's look at this example. It says, while driving, Miss Darwin observed a bug striking the windshield of her car. The bug hits the windshield and the windshield hits the bug. Which of the forces is greater? Which one's going to experience more force, the bug or my car?
Equal.
Neither, equal, perfect. Okay, this is a common misconception, and I promise somebody's going to get it wrong on the test. Somebody's going to do it. Don't let it be you, but somebody will. Happens every year. Doesn't matter how many times I say it, somebody's going to get it wrong. Okay, because you look at this and you're like, well, the car's fine. The bug, though, not so much. Okay, and so it makes you think that the bug must have experienced more force. But again, it is a force pair. This is Newton's third law. Okay, if the bug and the windshield are touching each other, the forces are equal and opposite. Now, their masses are nowhere near one another. And that leads us to the second question that I have. Which experiences greater acceleration? Is this the same? No. Okay, if the forces are equal, and we just got this new equation, F net equals ma, then that means the force on the bug equals the force on the car, which means the mass times acceleration of the bug equals the mass times acceleration of the car by substitution. Okay, and of course those masses are nowhere near the same. Okay, so I like to illustrate it like you see up here, so I'm going to make this little thing go away. I know it's Mr. Guthrie. All right. All right, so this right here, so it says the larger the mass, the less the acceleration because the forces are equal. So this is what I was just saying. The force that the car experiences equals the force on the bug. But the car has a large mass compared to the bug, which has a small mass. In order for this equality statement to remain true, this large mass will have to have a small acceleration. This small mass would have to have a large acceleration. And so they do not have the same acceleration. They have the same force, but because they have different masses, they will have different accelerations. The bug with less mass will accelerate more than the car. In fact, your car, because the bug is so much smaller, you're not even going to notice a change in your speed. When you hit a bug, you don't slow down. Okay, your car doesn't like slow down whenever you hit. If you hit like a large animal, yeah, you're going to slow down, but not a bug. Okay, because it has such a small mass that the acceleration that your car experiences is negligible. The bug, on the other hand, his mass is so small that his acceleration is very large, and very large accelerations are very bad for living things. Okay, for you, for bugs, for anything that's alive. You don't want to have a very high acceleration because that's how you get injured, is if you have that change in velocity happen very quickly. All right, so let's go ahead and talk about how we can solve second law problems. Okay, so second law being F net equals ma. Okay, it sounds like an easy enough equation, but we've got some steps up here because although it sounds easy, it's not as easy as it seems at first. Okay, so again, I would strongly encourage you to write down these steps. Okay, so the first step is going to be to draw a free body diagram and label the positive directions. And I say directions because you need to keep in mind that you are analyzing anything horizontal and anything vertical separately. So you're going to have a positive direction vertically, you're going to have a positive direction horizontally. By convention, we usually define the positive direction as up and vertically and to the right horizontally, but you do not have to. It depends on that scenario. Okay, but that's step one. Step two is going to be to write two second law equations, one for the vertical direction and one for the horizontal direction. Those equations are going to be F net in the y direction equals mass times acceleration in the y direction, and F net in the x direction equals mass times acceleration in the x direction. Okay, those are the second law equations I'm talking about, and you would write that for the horizontal and vertical directions separately. You have to analyze them separately, just like we did with projectiles. Okay, do we have to use kinematics? Sometimes when you're doing these calculations, you're going to have information in the question where you have, different forces, but then it asks you a question about, like, how fast is it going to be going after 12 seconds? Or it asks you, how far does it travel? And it brings in some of these other variables that we talked about when we did our kinematic equations. Those are the first 3 formulas on your AP Physics formula chart. Okay, and so sometimes you're going to get an acceleration, maybe using your net force equation, and then use it in a kinematic equation. Or sometimes you're going to get an acceleration from a kinematic equation and then use it in this equation. Okay, so your third question is, do you have to use kinematics? Sometimes you have to find acceleration with kinematics before you use F net equals ma. Step 4, solve. Okay, so let's look at an example. Again, I would encourage you to write it down so that you have something to look back at if you have issues when you're working through some of your problems in your task options for playlist 3, because this is your first set of notes in playlist 3. It says, a 75 kilogram person is riding an elevator that starts at rest and reaches a speed of 3 meters per second in 10 seconds while moving upwards. What is the person's normal force? You guys have been looking at elevators if you've been working on your checkpoint. Okay, so this may or may not sound familiar, but we're looking for the person's normal force. Okay, so again, step 1 is to draw a free body diagram and to identify our positive directions. Elevators only move up and down, so I only went ahead and labeled my positive direction in the vertical because I don't have any horizontal forces happening here. So there's not really a need for me to label it horizontally, so I just put my plus sign here. Okay, the forces acting on this person in the elevator would be the force of gravity because Earth's gravitational field is going to pull down on them, giving them their weight. So there's my FG. Okay, and then of course I have the normal force from the floor. But how long should I draw that vector? Should it be longer or shorter or equal to FG? How do you know that?
Because it's moving.
Not because it's moving. It's accelerating. Which way? Upward. It's accelerating upward because it moves from rest going up. Its acceleration is upward. It's not because it's moving upward. It's because it is accelerating upward. It's possible to be moving upward and have downward acceleration. Okay, and you would have to draw it differently then. So again, I need to draw it longer. I didn't draw it noticeably longer, but I did draw it longer than that one. If you want to exaggerate it and draw it really long, you could. Okay, but I have my 2 vectors here. That's the only things I have to draw. And again, I'm looking for the person's normal force. So my next step after I have my free body diagram was to write out my F net equations. And I don't have one in the x direction because there are no forces, but I'll go ahead and write it anyway. F net x is 0. F net y equals m times a in the y direction. Okay, F net is the sum of my forces. Keeping in mind that forces are vectors. So when I add them, I'm adding Fn plus Fg, but Fg is a negative number. Okay, so Fn plus negative Fg equals m times a in the y direction. Again, I'm looking for that normal force, so let's ask, well, before we rearrange it, do we need to use kinematics here? Okay, do I have the acceleration that I need? I do not. Okay, so yes, we do. So before we go any further with this, let's go ahead and take a look at what we know and how we can get this acceleration here. Okay, so we have x naught, x, v naught, v, a, t. It's the same list we've used before. I'm only dealing with things vertically, so that's helpful. I don't have to make 2 of these. But I'm going to assume that I'm starting at an initial position of 0. That my initial velocity is 0 because it says starts at rest. My final velocity is 3 and that it takes 10 seconds and I'm looking for the acceleration. I can use this equation here. V equals v naught plus a times t. If I want to solve for a, let's start by moving this v naught by subtraction. So now we have v minus v naught equals a times t. And again, to get a by itself, I need to divide both sides by t. So my acceleration is v minus v naught over t, which is change in velocity over time, which is the definition of acceleration. Okay, so I have a formula now that I can use to find my acceleration. If I plug in those numbers, I get an acceleration of 0.3 meters per second squared. Okay, so now I have my acceleration that is necessary for me to actually finish solving this problem. Anybody have a question before I go any further?
What's 4 plus 4?
Not related to this. Okay, now we can use the second law equation to find Fn. All right, so this is where we were, Fn minus Fg, because we were adding a negative. Let's just go ahead and say minus, equals m times a in the y direction. Again, we're trying to solve for Fn, so we're going to add Fg to both sides. And then Fg, guys, what is Fg equal to? Mass times, no, not negative 10. Mass times your gravitational field strength, okay, which you can use 10 for that, but it's not equal to 10. Okay, so mg.
Does it matter if you use 9.8? Or?
In the MyOpen Math stuff, it's going to want you to use 10. In your labs, use 9.8. All right, so I'm going to substitute that in. Okay, and now we can plug in some numbers. Okay, so I have Fn equals my mass, or this person's mass is 75 kilograms, times the acceleration we found earlier with our kinematics, 0.3, plus m times g. Again, I'm using 10 here. You're not plugging in a negative here. It was already listed as negative up here. We already took care of that. Okay, so whenever you go ahead and solve, that becomes 22.5 plus 750, which is a normal force of 772.5 newtons. That would be the person's normal force that they're experiencing. Their actual weight, Fg, was 750. Okay, so they feel heavier than they actually are. Okay, and again, that's part of what you're having to do in your checkpoint. But they feel as if they weigh 772.5 newtons, but they actually only weigh 750 newtons. Questions about the example? All right. So let's talk about an isolated two-object system. Okay, this type of system, like the one that's pictured up here, where you have, in this case, two blocks attached by a string going over a pulley. Okay, all objects will move in the same way because they're connected. So if this box moves, this one will too. Okay, at the same rate because they're connected by a string. Okay, because they all move together, we can analyze this as a no internal structure system. I don't know if you remember, we talked about two different types of systems, and we can use no internal structure for this just like we did with the other ones. That just means that it's easier for us to draw. Okay, we will only look at the linear motion of the system's center of mass. Although there will be a force of tension in the rope, it's now an internal force. If we consider our system to be both blocks and the rope, then tension now is inside of my system, and that means it doesn't show up on my free body diagram, and it won't cause acceleration of my system because it's an internal force. Okay, the only thing we draw on our free body diagrams are external forces, and those are the only things that can cause your system to accelerate. Okay, so we're going to do an example with an isolated two-object system. This one, if you want to copy it down to have one in your notes, might be a good idea. It says a massless pulley has a 1 kilogram block hanging on one side and a 10 kilogram block hanging on the other side. The two blocks are connected by a massless string and both are being held at rest. Once the blocks are released from rest, what is the acceleration of the 1 kilogram block? Okay, so they're holding them, they let go. Obviously this one's 10 kilograms, this one's only 1. You can see I already marked the acceleration on here. You probably already knew that this one, if it's, think of it like a tug of war because they're attached by a rope, this one's going to win. Okay, so it's going to accelerate in this direction, downward on this side, which means this side would have to go up, okay, in turn. So in order for us to analyze this system, it's easier to think about our isolated two-object system if we think of it linearly. Okay, and so I redrew it like this. Here's my two blocks. Here's my 10 kilogram and my 1 kilogram block connected by a string. But now I can see that, hey, if this one moves down, you know, this one's going with it. Okay, so you can, I guess, linearize your free body diagram, if you will. Okay, linearize your pulley system. But draw it so that you have it all in one dimension so that you can see what's happening, because you need to analyze it in just from one of those perspectives, okay, one of those frames of reference. All right, so again, first step, we're going to start with our free body diagram, and I labeled the downward direction this time as positive, and I did that because if I analyze it when it looks like this, it's going to go in that direction. So I may as well call the direction it's going positive. If you didn't want to label it that way, you don't have to. You can call that direction negative. You will still end up with the same answer at the end. Okay, so what is the acceleration of this block? That's what we're trying to find, but we need to draw our forces. So I'm going to have the force of gravity of this 10 kilogram block is going to be pulling it down. Okay, what's pulling against it? You can see it probably better on this picture. Okay, but this 1 kilogram block is pulling in the other way because it also has a force of gravity acting on it that's also pulling it down, but down from its point of view, if I flip it like this, is actually up. Okay, whenever I linearized my picture, that opposite force, okay, across my pulley is now up. And so that's my force of gravity of the other block that's giving some resistance, if you will, to its downward motion. So those are the forces that I need to include. It says that, I think it said there's no friction here. It says there's no mass to the string, so it wouldn't matter anyway. But we have just that. Okay, those are the only things we have to include here. Again, our next step is to go to our second law equations. This is actually the way the second law is written on the AP Physics formula chart. I like to write F net equals MA. The formula chart writes A equals F net over M. It's the same thing. Okay, so I'm still going to that step next. In the X direction, I don't have any acceleration because I don't have any forces or net force. In the Y direction, I do, and so here's my Y equation. A in the Y direction equals F net Y over M. Okay, F net Y, again, is the sum of my forces, Fg, which I called the positive direction, and then that means this is negative, minus Fg for the 1 kilogram mass. So I have Fg10 and Fg1 divided by M. Okay, so this is my F net right here. Again, Fg is mg, so I have, again, acceleration in the y direction is the mass times gravitational field strength for the 10 kilogram block minus the mass times gravitational field strength for the 1 kilogram block. Again, all of that divided by m. I probably should have put parentheses around this whole thing. If I plug in my numbers, it looks like this. So here's my 10 kilogram block, 10 times 10. Here's my 1 kilogram block, 1 times 10. You'll notice when I divided by mass here, this is the mass of the entire system. That's both of the blocks, which is 11. Okay, so this is a common mistake students make in this type of calculation, is not using the system's mass here. Okay, so make sure that you do that. Okay, if you solve these, again, you end up with 100 minus 10, so you end up with 90 divided by 11, which is 8.18 meters per second squared. Questions about this example? All right, guys, then that is it for the notes today over Newton's second law. For the rest of the class period, you can work on playlist 2, which is due by 11:59 p.m. tonight.